Hello guys, welcome to another video tutorial. Let's continue solving the problems of the chapter 3, problem 10. In the previous video, we solved this problem 9, and we did this parametric simulation. We changed the rotor position, the angle of the rotor, and we calculated the inductance of the coil. I hope you did this simulation before starting the next chapters: DC machines, induction machines, synchronous machines, and so on, because you can learn important concepts from this simulation: variation of the inductance, variation of the reluctance, torque, and so on. Anyway, problem 10. A reluctance motor with 4 rotor poles is shown in this figure. P 3.10. Yes, we have a rotating electric machine, a reluctance motor. The rotor has 4 poles and the stator has 2 poles. One pole here, another pole is here. Also, we have this coil, right? For the stator, half of the coil is here and the other half is here. Actually, we have half of ampere turns here and the other half here. The reluctance of the magnetic system is given here, this function. We have a constant term and a term that is a function of theta, the rotor position. So let me copy this. This is the structure of the motor, reluctance motor. This is the rotor core, and this is the stator. This is the mechanical angle, okay, theta. So for this structure, the value of the reluctance as a function of theta is given. So what is the magnetic equivalence circuit for this problem? Yes, when we excite this coil, for example, connect this terminal to the positive DC link and this to negative one, we will have a field in this direction. Okay? So similar to the problems of the chapter 1, you can consider one reluctance here for the back iron, one reluctance for the pole, reluctances that we have for air gap, reluctance for the rotor core, and so on. But the net value of the reluctance is given in this problem. We don't need to calculate these reluctances. So we have this magnetic equivalence circuit. We have this coil, this magnetomotive force Ni, and in total we have this reluctance R, that is a function of theta, a function of rotor position. So we will have this flux here in stator poles, this flux and this flux here, phi. Also, if we have symmetry, the half of the flux goes through here, phi divided by 2. The other half goes through here, phi divided by 2. But the phi is flux passing through one stator pole. Anyway, the coil has 200 turns and negligible resistance, and is connected to a 120 volts 60 hertz single phase supply. Yes, we can neglect the coil resistance and we know the value of the voltage, the RMS value of the voltage. Apply it to this coil. A, obtain an expression for the flux phi as a function of time. Yes, we have this equation. Voltage is equal to N d phi dt. This is the equation. The value of the flux linkage to this coil is lambda is equal to N phi. What is the value of the voltage that is equal to the EMF? Because we neglected the resistance of the coil is equal to N d phi dt. So what is the value of the phi? Like before, we should calculate this integral. Integral of V dt. If we neglect the DC bias, we have AC source, we have AC current, and we don't have DC bias for flux. So simply we can calculate this integral. If we assume this function for the voltage, 120 times cosine of omega et. 120 is the RMS value of the voltage. We should multiply it by the square root of 2. This is the peak value. Omega E is the angular electrical speed. So if we consider this function for the voltage, the flux will be integral of 1 divided by N V dt. So this is the value of the flux, the function. So what is the value of omega E? Is 2 pi times 60. The frequency of the supply is 60 hertz. That is 377 radian per second. If you replace this number into this expression, this will be the value of the phi. 2.25 times 10 to the power minus 3 sine of omega e t. So we calculated the phi, this flux in the stator pole, as a function of time. Okay, so this is important because in the next part we are going to calculate the torque using a new equation. So yes, the part B shows that the torque developed is equal to this one. 1 divided by 2 phi to the power 2 d reluctance d theta. Derivative of the reluctance with respect to theta. As you know, we have field quantities, we have circuit quantities, voltage and current. Also, we have these quantities from the magnetic equivalent circuit. We can derive different equations for calculation of the force or torque. How we can prove this equation? Yes, here you know that we can write this equation: N times I is equal to reluctance times phi. Yes, this circuit, the phi is equal to Ni divided by reluctance. So from this equation we can calculate I. I am going to use this equation to actually prove this one. We know that the torque, the magnetic torque, is 1 divided by 2 I to the power 2 times derivative of the inductance with respect to theta. So from this equation, we know the value of I, and we need to know the value of the inductance. The inductance is N to the power 2 divided by reluctance. So dl d theta is N to the power 2 derivative of 1 divided by reluctance. That is equal to this one. Negative of 1 divided by reluctance to the power 2 dr d theta. You remember derivative of this function, 1 divided by x. What is derivative of this function? Is, right, negative 1 divided by x2. And derivative of this function, 1 divided by fx, is equal to 1 divided by fx to the power 2 f prime of x. Okay, so this is actually the equation that I used here to calculate the derivative of the inductance and change it to derivative of the reluctance. So yes, here if you replace this derivative here and replace the value of the current, we will have this equation. The magnetic torque will be equal to negative of 1 divided by 2 phi to the power 2 dr d theta. Here again we have a typo error. We should have this negative sign. This is interesting. Yes, we can calculate the magnetic torque using this equation. The magnetic torque 1 divided by 2 I, the coil current, to the power 2 dl d theta if we calculate inductance. But also if we calculate reluctance, and if we know the reluctance as a function of theta, the rotor position, we can use this equation phi to the power 2 d reluctance d theta. Yes, equivalent method. And the part C, determine the values of speed, mechanical speed of the rotor at which the machine will develop an average torque. So here we can use this equation that we derived. We know the value of the flux, the phi, the pole flux, okay, to the power 2 times derivative of the reluctance. We have the reluctance here. Derivative of the constant term is 0, and we have this equation. Again, theta, the mechanical position of the rotor, the angular position is omega mt plus delta. So if you replace this instead of theta, we have this equation. You can simplify this equation, okay, using the equations that we had. How you can simplify this equation? Yes, sine of omega et to the power 2 times sine of omega m t plus delta. We investigated this equation before, so you can do the same calculations. We will have this equation for the magnetic torque. Okay, these three terms. Determine the values of speed of the rotor at which the machine will develop an average torque. So here we have three terms. We will have average torque when the omega m is equal to 0. In this case, the average torque will be equal to this one, this term. The maximum one is 0.5 Newton meter, because the average value of this function and this function are 0. We have omega et. In this case, because the rotor speed is 0, the mechanical power is also 0. What is the next speed? The next speed is this one. When we have average value for this term, okay, when the value of the omega m is omega e divided by 2. So in this case, these two terms, the summation of these two terms becomes 0, and the average value is equal to sine of, right, minus 4 times delta. What is the maximum torque in this case is 1 divided by 2 times this amplitude, that is equal to 0.25 Newton meter. For the negative omega e divided by 2 also we have the same interpretation for this term. Again, we have the same maximum average value. Again, as you can see, the average value of the reluctance torque depends on the initial position of the rotor, delta. Okay, the initial position of the rotor. In this case, the mechanical power is T times omega m, the maximum torque times the angular mechanical speed, that is 47.7 watts. Okay, so you can redo the calculations, prove this equation for calculation of the torque using reluctance and flux. In later chapters, for example, special machines, or in the next courses, electrical machine design courses, you will use this equation, right, multiple times, because you should propose the structure, calculate the reluctance based on the structure that you proposed for your design. So you can calculate the flux, the derivative of the reluctance versus the rotor position, calculate the average torque, and optimize your design. This is an important equation. Also, you can calculate the torque using the magnetomotive force, Ni, or F. Okay, so you can prove those equations similar to that are similar to this one. Anyway, let's go for the next problem. Problem 11. The rotating machine of figure 3.7, this figure in the chapter, has the following parameters. The self-inductance of the stator coil is 0.15 henries. Here in this structure, let me show the image. Here we have these two sections, rotating machines. We discussed this section, and cylindrical machines. Cylindrical machines are a category of electric machines. Here in this machine, we have salient poles, rotor poles and stator poles. In this case, as you can see, the inductance of the stator winding, the inductance of this coil changed by the rotor position. The inductance of this coil is a function of rotor position. So we have a reluctance torque, this equation that we discussed. Okay, this equation. But in cylindrical electric machines, in cylindrical rotating machines, the self-inductance of the stator winding and rotor winding are not functions of theta. And only we have this term for torque generation, this case. A cross-sectional view of an elementary two-pole cylindrical rotating machine with a uniform air gap is shown in this figure 3.7. In this figure, we have one coil on a stator. Yes, you can see the direction of the current out of the paper into the paper. Where is the magnetic axis? The stator axis is this one. Okay, because when you excite the stator coil, where will be the direction of the stator field will be in this direction. Okay, so suppose that the current in the rotor coil is 0. If we only excite the stator coil, we will have this magnetic field. Okay, we will have this magnetic field, and where we have the peak value of the magnetic field is here. Okay, the peak value. This is known as the stator axis in the direction of the peak value of the field generated by the stator coil. Similarly, if we set the value of the stator coil current equal to 0 and only excite the rotor coil, this will be the field generated by the rotor. Okay? So here we will have this maximum value of the field generated by the rotor that is in this direction. Let's generate a model in ANSYS Maxwell software before solving this problem. So let's save as this problem 11, and delete this design. I am going to generate geometry with arbitrary numbers. This simulation is also very important. You should do it. Here, suppose we have this rotor core, circle 1, the value of the radius. In this geometry, I am going to suppose these dimensions. We have this air gap thickness between the rotor and the stator. This is gap. We have this important diameter. This is the inner stator diameter, or ISD, inner stator diameter. Okay, inner stator diameter. And we have another parameter that is outer stator diameter, ISD, ISD, OSD. So this is ISD, inner stator diameter, this variable, and this is OSD, outer stator diameter. So is this diameter, right? This actually diameter, let me plot it here. This is the OSD. So here, let's set the radius of this circle equal to ISD divided by 2. Inner stator diameter divided by 2. I'm going to consider inner stator diameter equal to 60 millimeters. Okay. And generate another circle. This is the actually OSD divided by 2. We should here consider the radius, that is outer stator diameter divided by 2. OSD equal to 100 millimeters. Okay, so we can subtract these two objects. This is the stator, and we can add another circle. This is the ISD divided by 2 minus gap. The air gap thickness, let's consider 1 millimeter. This structure. So this is the stator. Okay, the stator, and this is the rotor core. How we can generate the geometry of the windings? I'm going to consider two slots in the stator core and the rotor core. So here, let's generate this geometry. Let's generate a geometry like this. Here, I am going to consider this polyline. Okay, this polyline. Rectangle 1, excuse me. This is simpler if just I use a rectangle like this, we should specify the width of the slot. So let's set the dimensions. Here, if I want to cut one slot from the stator, we can consider this rectangle to actually cut one slot from the stator. What is important is the depth of this slot and the width. Okay, this is width of a stator slot and this is depth of a stator slot. So here in parameters, I write the position, the x position equal to minus width of the stator slot divided by 2. Let's consider it equal to 4 millimeters. The x size will be width of the stator slot. The y size is actually ISD divided by 2 plus depth of the stator slot. Depth equal to 16 millimeters. Let's check. Here I used these two numbers, okay, to draw this rectangle. And here, let me reduce the depth of the stator slot to, let's say, 12, okay, or even a lower number, 10. 10 is good. This rectangle, we can duplicate and mirror it. Let's select the origin y-axis. Select these two rectangles, unite, select the stator, and then this rectangle, subtract, yes. So we generated the geometry of these slots. These parameters I considered in this case. Okay, this is the width of the stator slot, width of the stator slot, and this is depth of the stator slot. Anyway, now we can generate geometry for coils like before. Not too complex. Let me generate this coil arm and duplicate mirror it here. So this one, let's change the color and the material to copper. One coil for the stator. So let's change the material of these two objects to this electric steel. Save the project. I am going to excite the stator coil and calculate the field generated by the stator coil. How we can do that? Here we should select this object first, assign excitation. This is the number of turns for the stator coil times the IS, the stator current. Let's consider 100. This is a unitless variable. The current in the stator, let's consider equal to 4, okay, or 10 amps. We will check the field. So the direction of the current is out of the paper, and for this coil arm, again, we should define excitation. The direction is into the paper. Yes, out of the paper, into the paper. The direction of the field generated by the stator coil, okay, will be in the direction of the x-axis. Anyway, how we can generate the enclosure and solve the problem? We can draw another circle. Let's consider the radius of this circle equal to OSD divided by 2 plus 10 millimeters and change its transparency to 0.9, this region. So let's select the outer boundary, assign the zero vector potential boundary condition. That's all. Now we can add a solver to solve this problem. Okay, so analysis setup, analyze. We can calculate the field generated by the stator coil. So here, plot flux lines. Okay, uniform. You can see the flux lines and also the rotor and stator. We can plot the magnetic field B. Here, you know that because the thickness is lower than this part, we have a higher flux density. Yes, concentration of flux lines. This is the field generated by the stator coil. Where is the magnetic axis of the stator is here, right? Is in the direction of the x-axis of the global coordinate system. If you consider ns like a magnet, right? We for a magnet, for a permanent magnet, we have n pole, the s pole, north and south pole. So when we excite the stator coil, we have this field. We can do the same for the rotor. We can generate a coil for the rotor. So here, in this case, let me delete, or no, let me just, yes, let's delete and generate the geometry for the rotor. Similar to the stator, we can draw this rectangle object. Let's set the dimensions. This is negative of width of rotor slot divided by 2. And this is the y position, ISD, divided by 2 minus gap minus depth of rotor slot. This is again, let's consider 4 millimeters, and this equal to 10 millimeters. So this is width of rotor slot, and this is, let's consider ISD, this rectangle. Okay, so duplicate mirror it with respect to the ZX plane. We can select rotor, this and this one, subtract yes. We generated these slots in the rotor. Similarly, we can generate these rectangles for rotor coil. Duplicate mirror. Yes, again, let's change the color. We have this coil for the rotor, and we should define excitation. Here, let's assign this excitation. In this case, number of turns for the rotor, and this is the rotor current. Let's consider 100. Again, none. The value of the current equal to 10 amps. Yes, for the rotor. The direction of the current is out of the paper. For this one, we can define a new excitation, negative, into the paper. Yes. So now let's set the value of the stator current equal to 0, and also rotate the rotor. Let's select the rotor core and coil arms, rotate them equal to delta. What is the value of the delta? Consider it equal to 20. Yes, just I defined this parameter, for example, 50, to be able to rotate the rotor. So if I excite, right, the rotor only, like this one, the stator current is 0 and only we have rotor current. So let's analyze the structure and plot flux lines and flux density. So magnetic vector potential, you can see flux lines, flux density for the rotor and stator. Okay, this is the field generated by the rotor coil only. We set the stator current equal to 0. This is the magnetic axis of the rotor, is in this direction. Yes, the magnetic axis of a permanent magnet is in this direction. And now you can realize what is the rotor axis and what is the stator axis. This is theta, the angle between the rotor axis and the stator one. When the rotor is moving, we can write theta is equal to omega m t plus delta. Anyway, the stator and rotor windings are shown as placed on two slots on the stator and the rotor respectively. In an actual machine, the windings are distributed over several slots. Yes, in an actual machine, we have distributed winding, we have several slots. This is a simplified version. If the effects of the slots are neglected, the reluctance of the magnetic path is independent of the position of the rotor. It can be assumed that the self-inductances LSS and LRR are constant and therefore no reluctance torque are produced in cylindrical machines. Because we have a uniform air gap, the reluctance in front of the stator field is constant. Also, the reluctance in front of the rotor field is constant if we neglect the effect of these slots. So we don't have reluctance torque, and the mutual inductance LSR varies with the rotor position, and the torque produced in the cylindrical machine is this one. Yes, the torque is due to variation of the mutual inductance between the rotor coil and the stator coil. Okay, we don't have reluctance torque because variation of the self-inductances are negligible. Only we have torque due to variation in the value of the mutual inductance in cylindrical machines. This equation, if we consider this function for mutual inductance, we can calculate derivative and calculate the value of the magnetic torque explained in this reference. Again, these important numbers, right, are discussed, these conditions where we have the torque, the average torque. Anyway, so in this problem, the value of the self-inductance of the stator coil is given. The self-inductance of the rotor coil is given, and the mutual inductance is also given. That is a function of cosine of theta. Part A, the rotor is driven at this speed, 3600 RPM. If the stator winding carries a current of 5 amps at 60 Hz, determine the instantaneous voltage and RMS voltage induced in the rotor coil. Determine the frequency of the rotor induced voltage. So, if we set the rotor current equal to 0, yes, if we have open circuit for the rotor coil, yes, here we have two coils in this problem, the stator and the rotor. So if we apply, this is the rotor coil, and also consider this as the stator coil. If we open circuit the rotor coil and apply a voltage source to the stator coil and rotate the rotor at this speed, how much is the value of the induced voltage and induced actually value for the RMS value for the voltage, the flux and voltage? How we can calculate? We know that the flux linkage to the rotor coil is LRRIR plus LSRIS, the flux linkage due to the self-inductance plus the flux linkage due to the mutual inductance. We had this equation here in this part. This is lambda R, the flux linkage to the rotor coil. The rotor coil is open circuit, IR is 0, so the flux linkage to the rotor coil is LSRIS. Only we have the current in the stator coil. And here, as you can see, the value of the EMF in the rotor is equal to derivative of the flux linkage with respect to time, that is this one. So if we consider this current for the stator coil, the RMS value is 5 amps. The peak value is square root of 2 times 5 times sine of omega ET, the angular electrical speed. And this is the value of theta, the mechanical one. If you replace these equations into this equation for current and LSR, instead of theta, we will have this. So you can calculate derivative of this product, that is derivative of this function times this function plus this function times derivative of this function. Okay, you know that derivative dx of f x times gx, yes, this is equal to f prime g plus f g prime. You know that. So in this case, if you simplify the numbers, right, do the multiplications, we will have this induced voltage. Okay, so here we have omega m and omega e. The value of the omega m is this one, 3600 rpm. We should change it to radian per second, so we should multiply it by 2 pi divided by 60. This is 377, that is equal to omega e. So in this case, if we rotate the rotor at this speed, the omega m is equal to omega e. In this case, we can simplify this even more using these equations. Okay, using these equations. The value of the ER will be equal to this one. This is the peak value. Okay, what is the RMS value? Is the peak value divided by square root of 2. That is 150.8. And what is the frequency of the rotor induced voltage? Here we can calculate the frequency. This is the angular speed, right? 2 times omega e. I mean the electrical angular speed of the induced voltage in the rotor coil. That is 120 hertz. 2 times the frequency of the stator current. Okay, so this is important. The frequency of the current in the stator coil is 60 hertz, but the frequency of the induced voltage in the rotor coil is 120 hertz because the rotor is rotating. Okay, so we have a summation for the frequency of the stator, frequency of the rotation. Yes, and this is also an important point in this case. Yes, you can prove this mathematically, just mathematic, but we have this important point. You know that if the rotor is stationary, the frequency of the induced EMF will be the same as the frequency of the stator winding. Okay? But when we have movement, the frequency is different. Okay, so let's check numbers here for the chapter 3. This is the function, this is the RMS value of the voltage, and this is the frequency of the rotor EMF. The next part, suppose the stator and rotor coils are connected in series and a current of 5 amps RMS at 60 Hz is passed through them. Determine the speeds at which the machine will produce an average torque. Also determine the maximum torque that the machine will produce at each speed. So in the part B, the situation is different. We are going to force a current for the rotor coil. Okay, in this case we are going to connect the rotor in series with a stator. So here I am going to use this current source and connect the stator and rotor coils in series in this case. So we will have the same current for the rotor and the stator. So we know that the EMF in the rotor, right, the frequency, in this case, we have a current in the stator, current in the rotor. These currents are the same. And we have flux linkage variations for the stator coil and for the rotor. These are not important, right, to answer this part of the problem, because just we need to calculate the torque. And we know that the magnetic torque is Is times IR, derivative of the mutual inductance with respect to theta. This equation that we discussed. So Is is equal to IR. We have this function, okay, similar to the part A. The magnetic torque will be equal to this one, Is to the power 2, because Is is equal to IR, times derivative of this function, that is this one. If you use this identity, okay, if you use this identity, this equation, you can simplify this part, okay, and write it into this part. Also, we have cosine, sine. If you use this equation, finally, we will have this equation for the magnetic torque. We have three terms. In this term, we don't have omega E, but in these terms, we have omega E and omega M. So when the value of the omega M is 0, the average value of the first term is non-zero, is equal to minus 2 times sine of 2 times delta. The average torque depends on the initial position of the rotor. What is the maximum one? The maximum one is 2. Okay? And when the omega E, right? Excuse me, when the omega M is 2 times omega E, here, this term, right? The average value of this term is not 0. is sine of delta. What is the maximum one? Depending on the rotor position, that is equal to 1, the amplitude here. And similar one for omega m equal to negative 2 times omega e. You can check these numbers here. For these speeds, we have average torque. This is interesting, right? If we connect the stator coil and the rotor coil in series, so for these speeds, we will have average magnetic torque. Okay, so you can redo the calculations, okay, that we did for this problem and solve this problem. Also, you can generate the model in ANSYS Maxwell, right, to do the magnetostatic analysis, find the stator and rotor axis, and so on. So I hope you found the videos of this chapter useful for your exam. Let's continue solving the problems of the next chapter in the next video.